So I've got a number like the square root of 2. The square root of 2 is irrational, so how am I going to figure out what it's approximately equal to? Well, it turns out that it's approximately 1.414 and a bit more. But how would I ever figure that out? How would I know that that's approximately the value of the square root of 2? Let's use the intermediate value theorem to try to pull this. I want to use the intermediate value theorem to approximate the square root of 2. To do that, I'm going to use this function, f of x equals x squared minus 2. Notice something about this function. This function is equal to 0 when x is the square root of 2. Why is that? F of the square root of 2 is the square root of 2 squared, which is 2, minus 2, which is 0. So if I'm trying to approximate the square root of 2, one way to think about this is that I'm looking for a positive value that I can plug into this function to make it equal to 0. How am I going to find such a value? Now, the other good thing about this function is that it's continuous. And then I can plug in some values, like f of 1. Now, what's f of 1? That's 1 squared minus 2. That's minus 1. And I can plot that on my graph right here. That's this point right here. Then take a look at, say, f of 2. F of 2 would be 2 squared minus 2, which is 2. And I can plot that on my graph right here. It's 2, 2. Now, f is a continuous function, and at 1, it's negative, and at 2, it's positive. So it's a continuous function. It's negative at 1, and it's positive at 2. By the intermediate value theorem, there must be a point in between when the function's value is equal to 0. And you can see that on that graph. We're looking for that point. That is the square root of 2, where this graph crosses the x-axis, the positive x-axis. And that's the point that we're looking for, right? The intermediate value theorem promises me that there's a value in between where the function's value equals 0. And I can see that there must be such a point on the graph. And now I know that that value is between 1 and 2. And I can do better. I can cut this interval between 1 and 2 in half. And I get that f of 1.5. Well, 1.5 squared is 2.25 minus 2 is 0.25. Right, so that's, say, this point on my graph. Now what do I know? I know that the square root of 2, which is where this graph crosses the x-axis, is between 1, where the function's negative, and 1.5, where the function's positive. And I can do better, right? I can pick some other point. Let's be brave and pick 1.4. And if I plug in 1.4, well, 14 squared is 196. So 1.4 squared is 1.96 minus 2. That makes this negative 0.4. And it's just barely below the x-axis. And I can plot that point here. And now I know that the square root of 2, the positive input to this function, which is equal to 0, well, it must be between 1.4 and 1.5, because the function's value at 1.4 is negative, and the function's value at 1.5 is positive. So this is not so bad. I mean, we could do this with a few calculations on the blackboard. Let's bring out some sort of computation device so we can try to get an even better approximation to the square root of 2. So here I've got a function. The function is f of x equals x squared minus 2. And you can see that if I plug 0 into the function, I get out minus 2, because 0 squared minus 2 is minus 2. Now, this is a physical function. I've got this knob here, and as I spin this knob, the function's input value changes. So for example, if I spin it up to f of 0.5, f of a half, that's negative 1.75. That's right, because if I take a half squared, I get a quarter, and a quarter minus 2 is negative 1.75. And I could spin the input up to 1. F of 1 is minus 1, because 1 squared minus 2 is minus 1. Or f of 1.5, well, 1.5 squared is 2.25. 2.25 minus 2 is 0.25. Now this is positive, so I could wheel it back down a little bit. And I see that when I get to 1.41, the function's output is negative again. Then I could increase the function's input a bit. Oh, now the function's output is positive again at f of 1.415. And then I could decrease the input value a little bit. Now the function's output value is negative again, and I could increase the function's input value a little bit. Oh, now the function's output is positive. I could decrease the input a bit. Now the function's output is negative. Could increase the input a little bit. Now it's positive. Could decrease the input a little bit. Now it's negative again. Now look at what happened, right? What's going on? I'm looking at the function f of x equals x squared minus 2, and I'm walking back and forth across a point where this function is equal to 0. And as I walk to the left and to the right, the function's positive and the function's negative. And I'm getting closer and closer to the actual place where the function is equal to 0. And what is 1.41421356? It's awfully close to the square root of 2. And if you take the square root of 2 and square it and subtract 2, you get 0. What we just saw with the knob that I was turning, it's actually an incredibly general technique for figuring out where a continuous function crosses the x-axis. And we can do it very efficiently. Let's take a look at how we might do this a little bit more carefully. Here I've drawn a graph of some random looking continuous function, and I've labeled some points along the x-axis. Imagine that we couldn't see this whole graph. Just imagine that the only thing you can do is interrogate this function. You can ask this function at some input point, are you positive or negative? We're trying to figure out where, approximately, this continuous function crosses the x-axis. We're looking for a 0 of this continuous function. How might the game begin? I might begin by asking the function, are you positive or negative at 0? And the function's positive at 0. And then maybe I'd ask at 16. At 16, is this function positive or negative? And I'd see the function is negative. The function's value is negative at 16. Because it's a continuous function, and the function's value at 0 is positive, and the function's value at 16 is negative, I know that there's a 0 in between. There's some point in between that if I plug it into the function, I get 0 out. Now I could cut that interval in half. I could plug in 8, and I could ask the function at f of 8, are you positive or negative? And the function f of 8, the value of the function at 8 is positive. And now look, I know the function's value at 8 is positive, the function's value at 16 is negative, so by the intermediate value theorem, there must be a value in between, right there, where the function's value is 0. And now I could take that interval and cut it in half again. I could take a look at 12, which is exactly between 8 and 16, and I could ask the function, at f of 12, are you positive or negative? And the function's value at 12 is negative. So now I know, by the intermediate value theorem, the function's 0 of this function must land between 8 and 12. And I could cut that interval in half again. I could look at 10, and I could ask the function, well, if I plug in 10, are you positive or negative? And the function's value at 10 is negative. And now I know that the 0 must land between 8 and 10 because the function's value at 8 is positive and the function's value at 10 is negative, so there must be a 0 in between, a point where the function's value is equal to 0. Now I could cut that interval between 8 and 10 in half again. I could look at 9, and I could ask the function, at 9, are you positive or negative? And if I plug in 9, it looks like the function's positive. And that means that a value that I can plug into the function to make the output 0 lies between 9 and 10. And this is really quite remarkable. Right? I could cut the interval between 9 and 10 in half again and see if it was between 9 and 9.5 or 9.5 and 10. And I could keep doing this every time, getting a little bit more precision as to the exact value of the input that would make the function 0. The other really neat thing about this is that I could have just tried all of the values between 0 and 16. I could have plugged all 17 of those numbers into the function to figure this out. But by doing this clever cutting in half method, this bisection method, I managed to only ask 6 questions. Right? I asked the function's value at 0 and 16, at 8 and 12, at 10 and at 9. And by only asking 6 questions, I was able to narrow down a region where a 0 resided. Now, that's really quite efficient, much better than asking 17 questions. So this is a very general technique for figuring out where zeros of continuous functions lie. And I encourage you to pick your favorite function and see if you can approximate a root, a zero of that function.